Hi guys, this tutorial is on intermolecular forces. I know that sounds pretty boring, and at face value it probably is. But let me just tell you that basically everything in the universe is held together by the attraction of positive and negative charges. Your body itself has the shape it has because of intermolecular forces. The thoughts that you're having in your brain at this very moment are created by the attraction of one molecule to the next. And in fact, life itself would not be possible if it weren't for intermolecular forces. So let's take a look at some of the basic principles behind this topic. First of all, just to review, remember that there are charges in atoms and in molecules, and these come from protons, which are positive, and electrons, which are negative. And remember that unlike charges, positive and negative, will attract, and like charges will repel. And again, this is something you can just sort of memorize, and you probably should. But on the same token, at some point, you might want to ask yourself, why is that so? I mean, it's not really very fascinating if you just have to memorize it, but why do positive and negatives attract? What's going on there? And why should there even be positive and negative charges in the universe at all? That's a deeper question that maybe you might consider investigating at another level. At this point, we need to know that that happens, and let's take a look at some examples of that. So again, a single positive charge will attract to a negative charge. So a proton would attract to an electron. But also, an isolated charge, like a positive charge, can also be attracted to a neutral object, like, for example, your finger. If you held your finger near to a positively charged ball, the ball would attract to it. Why does that happen? Well, your finger has an equal number of positive and negative charges, has an equal number of protons and electrons. If you were holding a positive charge near to it, the electrons, which are free to some extent to move around, the electrons will move toward your finger. Will move toward that positive charge. And so the end of your finger will have a slight negative charge, and this is going to cause the positively charged ball to attract your finger. This kind of charge is called an induced charge. If you held a piece of metal near to a charge, it would be attracted even more because electrons are freer to move in a conductor, and you would get a greater connection there, or attraction, I should say. And so what we've created is an induced charge, and in the diagram that we're looking at here, you've created something called a dipole, because there's a positive end and a negative end to that structure. Okay, so positive and negative charges are what hold atoms and molecules together. We looked at earlier in ionic substances that there are positive ions and there are negative ions, and these attract to each other, and they create what's called a crystal lattice. These are very strongly held together. Some of the strongest bonds are formed between ions. It takes a lot of energy to break the bonds in an ionic substance. Molecules are formed when there's a sharing of electrons, and the electrons end up being within this sort of bond region, so you end up with a negative region between the nuclei, and this will draw atoms together and form distinct molecules. Covalent bonds are very strong as well, but not as strong typically as ionic bonds. Finally, metals are held together by freely roaming electrons. So the electrons are kind of zooming in around in here. As they do so, they kind of shift and move the electrons, and you get regions of negative charge being attracted to the positive nuclei of those atoms, and the result is a metallic structure that is held together. These are typically not as strong as covalent bonds or ionic bonds. All of these bonds are something that we've looked at before, and are forces of attraction that are in the actual molecule. So these are called intramolecular forces, or bonds. So this chapter is not focused on those. We've already looked at these. We're going to be looking here at the forces of attraction between the molecules. These kinds of forces are called intermolecular forces. So these are the forces that attract one molecule to the next. So for example, here's a hydrogen chloride molecule, and here's another one. These atoms are drawn together by a covalent bond. So that's an intramolecular force. But they are attracted to each other, and the force of attraction between these, which is shown here by that little dotted line, is called an intermolecular force. And these tend to be much weaker than intramolecular forces like covalent bonds and so forth. So let's take a look at some examples of some intermolecular forces. So anytime you have a polar molecule like hydrogen chloride, there's an unequal sharing of electrons, and so the electrons are going to get drawn from the hydrogen and pulled toward the chlorine, but they don't transfer over totally. They just spend more of their time nearer to the chlorine, and this gives the chlorine a slight negative charge, which we indicate by a delta negative. The hydrogen will consequently have a slight positive charge, which we call delta positive. This is sometimes shown with an arrow indicating the direction that the electrons move, and a little sort of plus sign down here to indicate the region where there's a positive charge. So a molecule like hydrogen chloride is called a dipole because there are two poles, positive and negative. If we place these molecules next to each other, they will be attracted by an intermolecular force, and in this case it's called a dipole-dipole interaction. When you dissolve an ionic substance like salt in water, the reason that the salt will dissolve, or the solute dissolves in the water, has to do with an attraction between the ions and the polar molecule, which is the water. And this is what allows in this case, the sodium chloride or whatever ionic substance you're looking at to dissolve into the water. So this kind of interaction involves an ion and a dipole, and so that's called a ion-dipole attraction. Now, water and other molecules that have hydrogen involved in a polar bond can have a particularly strong dipole-dipole interaction. This happens because hydrogen is sort of special in that the hydrogen atom, you recall, is just one proton with one electron going around the outside of it. So in a polar bond, like for example it's shown right here, the electron that the hydrogen has is being pulled toward, in this case, the oxygen, and that leaves a totally exposed proton here. And that allows another, for example, water molecule to get very close to that. And the negative charge of that, in this case oxygen, becomes attracted to the positive charge and the sort of exposed proton in the hydrogen. So this is a particularly strong intermolecular force called the hydrogen bond. Remember, it's not nearly as strong as like a covalent bond or an ionic bond, but it is a particularly strong type of intermolecular force. This will happen whenever you have a very electronegative element attached to the hydrogen. So as far as you're concerned, hydrogen bonding only happens when you have a hydrogen connected to a nitrogen, an oxygen, or a fluorine. Okay? And you remember that these are the most electronegative elements on the periodic table. All right. So hydrogen bonding can be used to explain a phenomenon that's shown here in this graph. You see that we have these three substances here which have particularly high boiling points compared to, for example, methane. And it doesn't make a whole lot of sense if you looked at that just from the standpoint of, say, mass. The methane would weigh, quite a bit, well, not quite a bit, but a little bit more than these other things here. So from that standpoint, I guess you would think that maybe that would be the hardest thing to sort of boil away. But what's happening here is the water, the hydrogen fluoride, and the ammonia are attracted because of hydrogen bonding. And this makes it more difficult for it to go from the liquid to the gaseous state, and therefore making the boiling points higher in these substances that have hydrogen bonding. All right. Another intermolecular force that can happen is called an induced dipole. So as in class, we did a demonstration where you take a charge and you hold that near to a neutral object like a ball that has some aluminum around it or something, and the electrons are sort of free to move from one side to the other in that ball, and you'll see a shift where the electrons will be on one side and the protons will be on the other side, or you'll get an excess of electrons on one side, and that'll cause this object to be attracted to that positive charge. But if you move the positive charge away from that, the electrons would simply go right back to their protons, and it would no longer have a charge. So this is called an induced dipole because we've created a dipole, but it's not permanent. It'll go away as soon as the charge is removed. This is what allows you to do a little trick here. If you charge a balloon by sort of rubbing it on your head, on your hair, or on a sweater or something like that, and stick it to a non-metallic wall surface, and the balloon will stick. And this is, again, because the electrons in the wall are being pushed away from the protons, and that'll create the surface of the wall will have a slight positive charge. If you took the balloon away, the electrons would simply move right back. So we've induced the charge, and it's only temporary. So in chemical systems, there's some examples where this starts to happen. If you have an ion in a, let's say, nonpolar liquid like hexane, the negative charge on this chlorine will push the electrons to the opposite side of that molecule, and we'll end up with a positive and negative side to a normally nonpolar molecule. So this is called an ion-induced dipole. So another example would be you have a permanent dipole like acetone, has a delta negative on the oxygen, and this will repel electrons in the hexane, a nonpolar substance, and again induce a dipole in that molecule. So that's called a dipole-induced dipole. Finally, if you have two nonpolar molecules together, let's say some octane and some hexane, and you put these together, basically they're not going to be attracted at all to each other, but it's possible that in a brief instant of time you may have a shift of electrons that just even temporarily are maybe more on one side than the other. These will induce or cause the electrons on the adjoining molecule to shift to the other side of that molecule, and this will create a slight charge or dipole. This kind of interaction is called dispersion because we're sort of dispersing or moving those electrons. It's a very, very typically a pretty weak type of intermolecular force. We can use this type of explanation for dispersion to explain why something like helium has such a very, very low melting point. And so helium only liquefies at a couple of degrees above absolute zero. And so what happens there? Well, when you get helium really, really cold, the atoms are basically hardly moving at all. So they have very, very little kinetic energy. And the electrons are sort of whirling around here. Let's just change color because that's not shown very well. So here's the electrons are moving around, and you can imagine, and in a certain instant, that you end up with a couple of electrons that are maybe on one side of the atom, and this will attract just for a brief instant to that proton over there, and that'll draw them together. So this has created a sort of a dipole. And it's just enough for something like helium at a very, very low temperature to draw those atoms together and form it into a liquid. Otherwise, it probably would never form into a liquid at all. Okay, so this is again called dispersion, sometimes called London dispersion, named after the scientist who came up with the idea, a guy by the name of Fritz London, not the city actually. So. Now, dispersion is one of those things that is typically a pretty weak force of attraction, but as the molecules get bigger, or if they have lots of electrons in them, then you have a greater ability to shift the electrons from one side to the next. And so, for example, if we look at these two substances here, both of them are pentane, but the normal pentane, N-pentane, which is in a straight line, has a boiling point of 309 K, whereas the neopentane has a lower boiling point, and the only thing that's different here is the shape. Well, the N-pentane has a greater ability to move or shift the electrons to the opposite side, and this allows you to create a dipole in this molecule a little bit easier than in this shape here. It's difficult to really move the electrons around and disperse them. So that would mean that N-pentane has greater intermolecular forces and therefore has a higher boiling point. And analogy might be made to, if you have like 12 kids in a bus, you could shift all of the kids to the back of the bus, and that'd be like the electrons in the back of the molecule. But if you had 12 kids in a VW bug, it'd be pretty hard to move them around, and therefore you wouldn't have any sort of dipole set up there. Okay, one of the rules to consider here is that typically dipole forces are more important than dispersion in most cases, and that's true if you're looking at molecules that are similar in size. However, if you're comparing two different molecules and one is a lot bigger, there's a big difference in size, then dispersion becomes more important. So that comes up to play in some cases in certain problems where you're asked to predict, which substance might have a higher boiling point and melting point, and we'll look at an example of that in a second here. All right, so this slide is just a summary of the different types of intermolecular forces, more or less in terms of how strong they are, but not exactly. So here we have ion dipole, and we have hydrogen bonding, like you have between water molecules, for example. Dipole-dipole interactions, like between these two substances. And we have an ion-induced dipole, like you might get between an ion of iron and oxygen molecule. Dipole-induced dipole, so we could have a dipole like hydrogen chloride and a normally nonpolar molecule like chlorine. Dispersion interaction between two fluorines. Okay, so if we look at this little diagram down here at the bottom, we can try to take these pictures and match them to the type of intermolecular forces that are being shown in the chart. This first one actually really is not an intermolecular force. That's really would be depicting the attraction between a positive and negative ion. So that would be an intramolecular force or an ionic bond. But starting with B, we have an ion connected to a dipole, so that's ion dipole. In the bottom one here we have an ion creating a dispersion in a molecule, so this would be an ion dipole, or sorry, it'd be an ion induced dipole. Here we have a dipole-dipole interaction. Here we have a dipole induced dipole. And this last one would be an example of London dispersion. Okay, so we have a worksheet that I gave you in class, and the first thing I asked you to do was take a bunch of molecules and try to separate them based on these two categories in an attempt to try to organize them and the type of intermolecular forces that exist between them. So first thing we did is to distribute the molecules in terms of things that do not involve ions. So all of these things here did not involve ions. We had solid water, neon liquid, liquid ammonia, bromine, hydrogen sulfide, and some formaldehyde. Over here we have substances that are involving ions. We got magnesium oxide, we have some lithium chloride, and then sodium carbonate and potassium chloride here. So based on this, we can divide those, and over here we can see that both magnesium and lithium chloride only are involving ions, and the sodium carbonate and the potassium chloride are both aqueous, so these are involving both a molecule and an ion. And then on this other side we have things that do involve hydrogen bonding and things that don't involve hydrogen bonding. Alright, the next thing that you were asked to do was to follow and answer the questions down below, so let's take a look at some of the results of all that. Okay, so right here you were asked to draw a picture of the crystal lattice for the substance which had the highest lattice energy or melting point, and that would happen in the magnesium oxide because of the charges. Magnesium has a +2 charge and oxygen has a -2 charge, and because of Coulomb's law, that means that the attraction between those atoms would be particularly strong, and so here we would expect the magnesium oxide to have a higher melting point than lithium chloride. Again, this is an intramolecular force. That's an ionic bond, but it's good to look at it just to see how it fits in the scheme of things. Okay, so now if we look at what's happening when you dissolve something like potassium chloride in water, the potassium and the chlorine will separate into ions, and these will be attracted to the water molecules. The positive ion, the potassium, is going to be attracted to the negative oxygen, and the chlorine will be attracted to the hydrogen. All right, if we're comparing ammonia and water, water will have a higher melting point, and that's because the electronegativity between hydrogen and oxygen is bigger than the electronegativity between hydrogen and nitrogen, which means the dipole in water molecule is more exaggerated than in the ammonia, and this will create a bigger, greater intermolecular force. So water has a higher melting and boiling point than ammonia. If we're looking at hydrogen sulfide and comparing it to formaldehyde, there's no hydrogen bonding here because the hydrogens are not connected to nitrogen or oxygen or fluorine. So this would be called a dipole-dipole force, and the formaldehyde would have a higher melting point because, again, of the greater electronegativity between the carbon and the oxygen compared to the hydrogen and the sulfide. Finally, if we're comparing the melting points of neon and bromine, you would expect that that bromine would have a higher melting point, and that's because it's a bigger molecule. Both of these are nonpolar, but the bromine is a diatomic molecule, so there's more electrons just in general, and it's an easier shape to push the electrons away, creating a dipole. That increases the intermolecular force, and therefore it will have a higher melting point. Okay, so that's I'll look at pretty much all of them, and you should be able to draw pictures of these different types of intermolecular forces on an upcoming exam, and hopefully the different terms for each of these make sense. All right, finally, there are some phenomena that we see, particularly in liquids, that relates to intermolecular forces that are worth taking a quick look at. Surface tension is created by intermolecular forces. There's an uneven distribution of force at the surface of a liquid, and this creates a sort of almost like a thin film on the liquid, which makes it appear to be a little bit stronger than the liquid itself. And this is what allows insects, for example, to kind of skirt across the surface of water, or it also allows you to sort of float paper clips, for example, on the surface of water as well. Viscosity is the tendency of a liquid to resist flow, and this is also due to high intermolecular forces. So things like syrup and honey are things that have high viscosities because they're thick and sticky. Okay, so I hope that helps. That's just a summary of the different types of intermolecular forces, and good luck with your studies.